If an atom were enlarged to the size of a classroom, its nucleus would be the size of a pinhead. Almost the entire volume of an atom is empty space, yet that vibrating center contains more than 99.9% of the atom's mass. Uranium-235 is uniquely bulky. Packed with 235 protons and neutrons, it sits on the precarious edge of physical stability. Inside that crowded core, the positively charged protons constantly repel each other via the Coulomb force, while the short-range strong nuclear force barely manages to hold the structure together. That constant internal tension makes uranium-235 a tightly coiled cosmic spring. It requires only the slightest external disruption to fail. That disruption arrives as a single free neutron. Because it carries no electric charge, it drifts through the atom's outer electron cloud without being repelled. When this particle strikes the core, it is instantly absorbed, triggering a neutron-induced reaction. The addition of that single particle transforms the core into a new, highly unstable isotope, uranium-236. This extra mass and energy overwhelms the strong nuclear force. The nucleus begins to wobble rapidly, stretching from a sphere into an elongated, trembling liquid drop that can no longer sustain its own structure. The nucleus snaps. It fractures into two distinct intermediate mass fragments, typically forming elements like barium and krypton. The collapse ejects 3 rogue neutrons, kicking them away from the fracture site at high speeds. We can map this transaction exactly. 1 neutron and uranium-235 produce the excited uranium-236, which then breaks down into barium, krypton, and 3 loose neutrons. Comparing the mass of the starting materials to these final fragments reveals a measurable loss of physical matter. The ledger doesn't balance. Adding the precise mass of the barium, krypton, and 3 neutrons, the total is lower than the starting mass of the uranium and the initial neutron. The final products weigh less than the ingredients that created them. Physicists define this missing weight as the mass defect. Explaining where that matter went requires Albert Einstein's theory of special relativity. E equals mc squared establishes mass is energy. The missing mass converts directly into the violent kinetic energy propelling the fragments outward. Fission represents the hyper-efficient conversion of physical matter directly into raw energy. The universe favors states of higher stability and tighter binding. This atomic stability map shows uranium weakly bound at the far right tail at 7.6 mega-electron-volts. By fracturing, lighter elements jump to the stable middle region. This difference releases approximately 200 mega-electron-volts per atom. The power of fission is the result of a heavy atom finding a more stable configuration. While one atom is microscopic, the 3 rogue neutrons ejected during the fracture change the scale of the event. These neutrons act as new projectiles, striking adjacent uranium atoms and multiplying the reaction exponentially. When moderated, this cascade provides the sustained heat for a power plant. Unconstrained, it triggers the instantaneous release of an atomic weapon. The microscopic conversion of missing mass and binding energy dictates the most extreme manifestations of power in human history.